Okay, everybody, we're getting underway here. So this evening we start content here from chapter 10, where we're looking at gases. Our overall sequence of where we are at, where we're going, beginning with chapter 5. In some ways, our story begins there, where that was aspects of looking at energy, but it definitely had a important starting point with chapter 6. That's where we were looking at the electronic structure of atoms. And I say starting with that, what pretty much happens is we see how that then leads to periodic properties for atoms in chapter 7. We begin to have the atoms now stick together and form bonds. That's described in 8. Chapter 9, we look at more in depth those bonds that are being formed, how that influences the shape of the molecule, whether the molecule has a dipole moment or not. So all of those ideas, to me, begin with chapter 6, are really all leading up to describing molecules, their shape, whether they're polar or not. To finish off the course here, now we're going to look at a collection of those molecules. What happens if we have them where they're quite far apart and not interacting very much? That's going to be described as a gas. What if they're together, but there's still a lot of dynamics to their motion? That's going to be a liquid. What happens if they stick together and it has more of a constrained symmetry, a more constrained shape to it? That's going to be a solid. So we really have this progression. Let's take the atoms, stick them together in bonds to have molecules. And in this last 3 chapters, we're looking now at those particular arrangements. So within this one, we're going to look at characteristics of gases. When I look within the breakdown here and where we're going, as far as our time here, I grabbed a couple images off the syllabus here. So at the top, we see the remaining class periods that we have, and at the bottom, the date for the final exam. So my perspective as I looked at this is we have very few classes left, okay? I got a plan, I think, to try to spend our time and look at ideas that are going to be most constructive leading into the final. Tonight, we're going to get through most of chapter 10. And in fact, with the remaining chapters, we cover these much quicker than we do chapters that were earlier in the semester. There are fewer ideas that you're going to be responsible for within these. I want to, as we're thinking about where we're at, headed into the cumulative final, in many ways, you're going to have far more questions on the final exam that are from chapters 1 through 9 than you will with the new ideas that we're coming to. So we got to sort of juggle both of those things. We want to see what does it mean to have some new ideas and skills that we add, but also revisit the ones that I think you've got a really good chance of being successful with that were earlier in the semester. So when I'm looking at our plan and where we're going, I grabbed this image here from Mastering Chemistry. So again, only 5 more classes remain. I don't know about you all, but these might be the last 5 I ever teach online. I'm teaching in person in the fall. I think OSU's back in the fall in a big way. So hang with me here, okay? We don't have that many that we need to struggle through in this online format. We know when the final exam is going to be. I've placed 3 different homework assignments that we have leading up until that final one. These are the last 3 Mastering Chemistry assignments that we're going to have in the course. I have them where I try to balance and bring in some new ideas from chapters 10 and 11. But in each of those cases, about half of them, they're questions from earlier in the semester. Chapters 2, 3, 4, 5. They're ones that were previous skills. Because I know that those earlier ones, they're really significant when we get to the final exam. And also, another way of trying to sort of think about that, this is what I have listed right now within perusal as we look for the rest of the semester here. Chapter 10 is what we're covering tonight. There's some that we have coming up pertaining to chapter 11, but you notice I put in a lot of these optional ones here. These are videos where I'm trying to direct you to what I think are the significant ideas that you should expect for the cumulative exam. These are all optional. If you want to give them a watch, give them an overview, see what you think. But I'm really trying to do what I think our cognitive scientists would tell you to do. It's not the optional part. It's how they're spaced out. They're delivered in stages. If you take these in small bites as we move towards the next 2 weeks here, I think that's a really good way to recall that information. So there are ones where I'm trying to tell you what I think are most important in chapters 1 and 2, 3, 4, 5, right in stages. Now, I know, I mean, as a student too, I know it's like, well, I'll do that right before. Man, on a cumulative final, you can't try to do it in the last couple of days. So these are optional ones that are listed. I think that they're going to try to point you to the most important ideas in each of the different chapters. I think that many of those ideas early on, they're going to seem a lot easier to you now than it did before. We've been doing so much with the different skills when it comes to naming or different things. You're going to see some that you want to get back the your skill at. Some you might learn a little bit more, but I think you're going to really find in a good way that you have a lot of those skills already. So if we look at where we're headed then this evening, there were 2 pre-class videos that people were making some really good comments on. First one was looking at general characteristics of gases, and the second was looking at an introduction to the kinetic molecular theory. So in both of those cases, I'm going to pick up on those ideas and extend them a little bit in class. In this in this section here, where we're looking at the ideal gas law and what are called an idea called partial pressure, we're going to be doing calculations on those. So in a way, we've got an aspect of calculations that we're going to be practicing, and then what I would say is more conceptual, which is the kinetic molecular theory. So that's what we're up to tonight. So let me ask you a question, because it's going to help me as far as how we allocate time. When it comes to seeing calculations in class, I'm going to be working through, I'm going to be setting a few up. How do you think you're going to interact with them? So if I say, okay, here's a problem, give it a try, are you more likely to just wait until it's shown? Will you think about it and try to get started, or try to finish it? And the reason this is important is this helps me decide how to allocate our time. If everybody just says, well, I'm just going to wait until you show me, there's no reason for me to give you a chance to try it. So share your view on this. This is going to help me decide how to spend our time tonight. Take about 10 more seconds. Okay, sharing results with y'all. For the most part, a majority, over half, are saying you're at least going to try to get started with it. You'll think about it. I think that then informs me. I'm going to give you some time within the different ones so you can start that. If I shortcut it a little bit, if I say, okay, get started on it, and then I jump in, I think that will still serve you, because you'll still begin processing the information. Now, this class, this lesson this evening, and for gases in general, I think it really has 2 different sets of skills. One is being able to work through equations and do calculations. And the second, at the end here, it's a lot more about the ideas and the concepts. So I think in a good way, it brings together very different skill sets. So it allows people to have strengths in different parts of the chapter. So let me first go through ideas that were in the first pre-class video. This idea is, if we're trying to think about characteristics of a gas, our gas particles, when we have our molecules there, they're mostly empty space. It's homogeneous throughout, and the particles are in motion as they just move around randomly and bounce into each other. When we think about the states of matter, if I think about a liquid evaporating to become a gas, what I want to keep in mind is I'm not breaking any bonds in that process. I'm separating out the water molecules, but I'm not breaking any of those internal bonds. We were looking a lot about the energy of bonds, the formation of bonds in chapters 8 and 9. We're not talking about breaking those bonds. We're talking instead about separating out the molecules from each other. The kinds of elements that we're going to see within our gases here, well, our noble gases are all examples. We have quite a few of diatomic ones that we've been thinking about. If we look at this list here of the molecules that we're going to see as gases in this class under temperatures and pressures that are everyday conditions, they're almost all these simple, small molecular compounds. We're going to learn a little bit more why that is the case when we finish up chapter 10 and begin chapter 11. But for now, when we think about gases, for the most part, there are these very small, simple molecules. Nearly every gas that we encounter in this class is going to be something like that. When we think about their properties, we began this whole course looking at properties of matter. That was back in chapter 1. On this idea of, well, does a gas have mass? Well, if you took a balloon, you inflated it, would you be changing its mass? Most folks within the video said, yeah, you'd be increasing the mass, and I agree with that. Helium particles have their matter, they have mass. If I add more to the container, the mass goes up. Yet we know that helium balloons float because their density is less. Their density is less because the volume is going up more than the mass is going up. This idea of we don't want to confuse mass with density. I brought this up once, so I mean, you can probably feel sorry for her. So my daughter right now, she just finished working. She just finished her schooling down at Cincinnati, and she's just taken a nursing job. But she was about your age, and I remember I was at the pool with her, and I said, and with her friends, and I said, so tell me, do you think you are more or less dense than water? Now, she knows me well enough to give me a look like, Dad, we're not going there. But I find it remarkable how we are so closely matched to the density of water. We are so closely matched where if you either breathe in or breathe out in the pool, you can change whether you're sinking or floating. Our density is really close to the density of water. In our mass, I mean, mass and density, we don't want to confuse the two. When we're thinking within this, particles of matter, as gases, definitely have a mass. They exert a pressure. You may have heard of the atmospheric pressure. Where that's coming from, comes from this experiment right here. So the idea was that Torricelli filled up a tube, spherical tube there, open at the bottom, filled it up with mercury, put his thumb over it, submerged it into a pool of mercury there, and measured the height of it. And he did the experiment many times, and it always was reaching to the same height. This was baffling to them. How high did it reach? 760 millimeters is how high it reaches when you're at sea level. That's our definition. He's making the first barometer there. That's our definition of what a torr is. Millimeters of mercury, it's the same unit of pressure as what a torr is. Our idea here is that the atmosphere is pressing down on that pool of mercury, and it's holding suspended this column there. So idea within this one, we want to know units of pressure, both ATM and torr. We're going to see quite frequently doing conversions between the two. So if it says a gas has a pressure of 785 torr, what would be its pressure in ATM? You could just set up a proportion. It's a little bit more than 1 ATM. So as far as the units, you'll also see units like Pascal, but I know the only two you're going to be responsible for are atmospheres and torr, and being able to do conversions back and forth between those two. Now, if we take our gas, put it in a balloon, I'm going to consider a balloon to be a flexible container. Back in chapter 5, we looked at gases and things like pistons. I think those were also, the volume could change. So our thought here is, as we begin to think about this, when would the pressure inside this flexible container be different from the pressure outside? My point within this one is the volume of a flexible container changes when the pressure is different. So like when we had our piston there, if we made the pressure greater on the inside, the piston would expand. If the pressure was less on the inside, the piston would contract. So this idea here is a change of volume in a flexible container, that tells me the pressure is different. This idea of being able to begin to think about it, I'm thinking about the gases here in terms of the forces, how I could have a force inside the balloon being countered by a force on the outside of the balloon. If those forces are equal, if the push on the inside is equal to the push outside and the volume of the balloon isn't changing, that tells me the pressure inside is equal to the pressure outside. So if we look at then a few relationships amongst these ones, so gases exert a pressure, they fill up a container and have a particular volume. We can talk about how much of the gas is there and the temperature. So the units that we're going to see, our pressure is going to be given symbol P, and we're going to want to have that in atmospheres. The volume, that symbol V, we want that in liters. N, that's our symbol for number of moles. Capital T, that's the temperature. We're going to be using Kelvin for our scale. I know this was introduced way at the start of the semester, but we really haven't done any temperature conversions. We need to now. We need to know that 0 degrees Celsius is 273.15 Kelvin. So I've just introduced two things that I want you to memorize. I want you to be able to do conversions between Celsius and Kelvin. And here's our conversion right there. 0 degrees Celsius is 273.15 Kelvin. So usually if it's given in Celsius, I'm going to add 273.15 to it. And I also mentioned we need to know conversions between atmosphere. 1 atmosphere is 760 torr. Another thing to add as far as a definition or description is what's called standard temperature and pressure, or sometimes you see it listed as STP. Those are conditions of 1 atmosphere, and the temperature is 273.15. So add that to your list of things to know. Conditions of standard temperature and pressure are 1 atmosphere and 273.15. Now, when we're thinking about relationships amongst these and experiments that might go along with those, these are the kinds of things that we could use to explore. Simply putting gas into balloons, changing their temperature with something like liquid nitrogen, placing them into bell jars where we can evacuate the air around them. This tells us a lot about the different relationships. If you take a balloon and put it in a bell jar, you use the vacuum pump to remove the air from the outside there. What you find is that the balloon expands. It expands to fill up the bell jar container there. So how do we begin to explain that? Why would the volume increase? Well, the volume changed because I changed and the pressure inside the balloon was no longer equal to the pressure outside. That's what leads to the volume change. I reduced the pressure in the bell jar that was on the outside by removing the air from there. The pressures were no longer equal, so the force inside the balloon was greater than the force outside. The balloon's volume increases until eventually the pressures end up being equal once again. There's an inverse relationship here between the pressure and the volume. If something, as we just saw here, within our balloon case right there, the volume was getting bigger inside the balloon and its pressure was decreasing. So in terms of pressure and volume, when one goes up, the other one's going down within our relationship. How about the temperature? There's a lot of videos you can find involving liquid nitrogen in balloons. I just grabbed this one. There's many on YouTube. He's putting a balloon into liquid nitrogen. Liquid nitrogen's at 77 degrees Kelvin. Right away, you see the balloon begin to contract. So here we're seeing a relationship between temperature and the volume of the balloon. I would say we've seen a relationship between temperature and the pressure, because I think the volume of the balloon is changing because the pressure is changing. Why did the volume of the balloon decrease in this case? I think we cooled it down. The temperature inside the balloon decreased. The force inside the balloon was now less than the force outside. The pressure inside the balloon was less than the pressure outside. This caused the volume to decrease until the forces are once again equal. So in this case, we're seeing a direct relationship between the volume and the temperature. If the temperature goes down, the volume goes down. Temperature goes up, the volume goes up. And it also gives us a clue why we're going to want to be in Kelvin. If we're on Celsius, we're going to quickly run into negative values for the temperature. That's going to mess us up with our calculations. If we're in Kelvin, we're always going to have positive values. We can only go down to 0 degrees Kelvin. And in fact, for gases, it's not going to be a gas once we start getting that cold, but we would run into negative values otherwise for some gases. So that's why we're going to be in Kelvin. So I quickly went over a few relationships there then. Those are summarized in our ideal gas equation. Our ideal gas equation brings together several of those variables that I just mentioned. On the left-hand side, we see pressure and volume. On the right-hand side, N was number of moles, T was the temperature. The R, we can consider that to be a scaling factor. That's called what's called the gas constant. Notice the units that we have here for the gas constant: liter, atmosphere, mole, and Kelvin. This is a constant that will be given, but I find in this chapter, I quickly memorize it because I'm using it quite a few times. This tells me that all of the different variables in this equation are going to work and fit together if I'm in liters for the volume, atmospheres for the pressure, I'm involved with moles, and the temperatures in Kelvin. This equation right here, it summarizes the different relationships that we saw within those demonstrations. Holding the other values constant, when the temperature went down, the volume would go down. They're on opposite sides of the equation. Pressure and volume are on the same side. If the pressure goes up, the volume would go down, keeping the other terms constant. You might be familiar with these different relationships, perhaps Boyle's law, Charles's law. Those are looking at specific subsets of these. You're not going to be responsible for those names on the test. We'll simply be able to use the combined form, which is our ideal gas equation. And remember, let's add to it our description for STP, standard temperature and pressure. That was 0 degrees Celsius, which would be 273.15 Kelvin, and 1 atmosphere. Okay, so I quickly went over a setup of ideas that we had within that first video. Let me now begin to show you some calculations that we can do. So first of all, let's look at the volume of an ideal gas under conditions of standard temperature and pressure. So the pressure would be 1 atmosphere. The temperature, in that scenario right here, we're going to be calculating these volumes. It's listed at 0 degrees Celsius, so we know we need to convert that. If we want to calculate the volume for our missing term here, we would have to calculate it and take the temperature from Celsius into Kelvin. Now, in that scenario, they put in 4 grams of helium, 28 grams of nitrogen gas, or 16 grams of methane. Each of those amounts, those masses, they chose those for a reason. Because each of those, if you use the molar mass, they used 1 mole in each of these scenarios. So what we're comparing here is, what would be the volume of 1 mole of helium at STP, standard temperature and pressure, or 1 mole of nitrogen gas, or 1 mole of methane gas? In each of those, if we look at the variables, they're all the same pressure. They all have 1 mole. R is a constant, and the temperature we can convert from Celsius to Kelvin. We only have 1 variable left, which would be their volume. So if I looked at those terms, I could have chosen this for any of these. I've got 1 atmosphere. I don't know how many liters it is, but it's for 1 mole. Here's my gas constant, R, and it's 273.5. So for all of these, if I calculated it, they all get exactly the same volume. This is the volume of any ideal gas at standard temperature and pressure. This is another thing that might be helpful to know. This will help you on some of the calculations that we've come across. Any ideal gas under conditions of standard temperature and pressure, remember that was 1 atmosphere and 273.15 Kelvin, it has this same volume, 22.4. Add that as another detail. I'm trying to build up details along the way that are going to help you with these calculations. Now, one thing conceptually that's important here, it's not the mass of these particles that somehow was important. In all of these cases, it was simply the number of the molecules, not their mass, that they determined the pressure. That's something we're going to explore a little bit later tonight. But this idea of what contributes to the pressure, if we look at that equation, PV equals nRT, N was the number. There's no relationship there telling me the mass. So if we want to look at the relationships within PV equals nRT, mass isn't showing up in that. That's one thing that we're going to explore. We see that many gases here, if I'm looking at CO2, N2, helium, they all have a volume really close to that value of 22.4. That tells me that all of these gases, they behave really close to the ideal gas law. Now, is there any difference? I said that if we're looking at the pressure, it's only the number of the gas particles that's important. How about something like density? Look at these scenarios right here. Let me send you a question on this. When it comes to helium, nitrogen, and methane, under conditions of standard temperature and pressure, are the densities the same, different? Do you know what to look for? See if you can rank that. Can you use the information on the screen to rank these in terms of their density? Which one has the highest density? Which one has the smallest? Take about 10 more seconds here. If you don't know what you're to look for to try to answer this question, I got that as an option too. So sharing results with y'all. As far as choosing a specific one, we have the most common here is saying that nitrogen gas has the greatest density, and the helium gas has the smallest. If we look within this, or some folks are also saying not sure exactly what to look for. Let me talk you through this one. So as I look at this, each of these have the same volume at STP. Standard temperature and pressure, they all had the same volume. They all have the same number of particles. But then if I look at the mass of those particles, those are different. The mass of the gas was different because the mass of a helium atom is different than the mass of a N2 molecule. So I completely agree with the folks that had this as their ranking. When we're thinking about the density, density is one feature where the mass is going to be important. We saw that pressure was not, but the density is. So that's one thing that we sort of want to keep track of both this evening and when we finish up chapter 10. Keep track of, is the property something that depends on only the number of the particles there? Or does it also depend on a feature of them like their mass? Density is one where the mass of the particle is going to be important, but the pressure, it turned out, was not. I'm going to show you a few different types of calculations that I would expect for this feature. And as far as where we're at in the chapter, we're about halfway through the chapter. Okay, when I say that we can finish a chapter in about one night or so, within these, there's just fewer ideas or skills that we need to get to. These idea of typical equations involving gases. One thing is using PV equals nRT to calculate one of the missing terms. This would be an example. It says, consider having 12 grams of helium, placing a 5-liter gas cylinder. The container is going to explode if the pressure reaches or exceeds 20 atmospheres. At what temperature would it explode? So if I look at this one, and if I look at all of them, if I'm thinking PV equals nRT, what I'm asking myself is, which terms do I already have and which ones are the unknown? If I only have one unknown, I'm sure I can solve for it. If I look at this one, my unknown is going to be the temperature. I see given a volume, a pressure, R is a constant, and I can use the molar mass of helium to determine the number of moles. If I were to set that one up as I would think about it, this would be the point where I would walk to the chalkboard and we'd work it through. Can't walk to the chalkboard. So let me show you my work within this one. Okay. You haven't seen my scribbles too often. This is exactly how I'd scribble it. And I sort of have a plan here. This is how I set up equations for this one. I write PV equals nRT, and then I write arrows that show me what terms I already know. In that question, it told me it was 20 atmospheres, 5 liters. R is my gas constant. N, I figured out how many moles. So I'm doing that math sort of on the outside of it. And I have one variable, which was the temperature. When I set this up on my piece of paper, and this is exactly how I'd solve it. This is obviously my piece of paper. For me, I always write the units for R because I want to mentally tell myself, hey, make sure you are thinking of liters. Make sure you are thinking of atmospheres. If I were to work this one through, this would be my answer here in Kelvin. And if I were to convert it, this would be the answer in Celsius. Now, if you're asking, well, are we supposed to report it in Kelvin or Celsius? My advice to you was, well, the question is going to tell you. My advice is try to always be able to get it to Celsius, because if you can get it to Celsius, you know how to do the longer portion of it. So you could always stop earlier and report it in Kelvin. I think on your tests, they're probably going to be asked in terms of Celsius. Okay. So this would be my framework. This is, I think, the easiest type of question for an ideal gas one. If I were to go 1 degree higher in terms of difficulty, it would be this one. Take a second, read that one for me. So within this one, I'm again thinking, okay, if I write PV equals nRT, what terms do I know? Which ones do I still need to figure out? I'm going to give you a minute or two to set this one up. I'll show you my work in just a second. Don't feel like you need to race and finish the whole thing, but see if you can read this through and begin formulating your plan. And then I'll share my plan here. Take about 90 seconds. Okay. I know that's a brief amount of time, but grab a pencil, grab some paper, grab a calculating device, see if you can begin to set that one up. Okay, so in order to set this one up, how I'd go about it, same strategy I would usually use, and you're going to see this quite a few times. I'm going to write the PV equals nRT part. Then I'm going to draw arrows to see, okay, which of these do I already know? Well, I know the value for the volume was given in liters. R, that's a constant, 0.08206 liter atmosphere per mole K. When I have to do my conversions, I write those on the outside. So I need to convert from torr, get that into atmosphere. So it's just a ratio. 1 atmosphere is 760 torr. So 735 over 760, that will tell me how many atmospheres it is. It's not quite 1. In order to convert to the temperature, get it into Kelvin, I'm going to take the 37 and add 273.15 to it. I've got one missing term right there. That would be N. That's the number of moles. So this same setup, this top one, that's how I set these up all the time. I just got one variable and I did sort of the conversions there on the outside. That will tell me the number of moles that I have. I would use Avogadro's number now to tell me how many molecules it is. Now, I'm putting air in quotes here. There are not, if you look on the periodic table, it doesn't say air. Air is going to be about 79% nitrogen, about 20% oxygen, but it doesn't matter what those molecules types are. because in our P equals nRT, the type of the molecule doesn't matter. It's just the number of the particles that I have. So a couple different takeaways within this one. We did some unit conversions. When I set this up, I draw the unit conversions just on the outside. When I'm trying to solve it, I make sure that I write out my R value and I include the units, just so I'm thinking that I need to have those correct. When I'm calculating that and coming up with something like molecules of air, once again, for our ideal gas law, it doesn't matter what type of molecule it is. A molecule is a molecule when we're plugging it into that. So this would be, I would say, 1 degree higher in terms of difficulty. The only thing that this question had that the previous question didn't have was unit conversions, where we had to do a little bit more. And I suppose we had to do a little bit more with the answer too. Instead of leaving it at moles, we had to convert to see how many molecules it would be. But this would be a high scoring question on the exam, I'm sure. Let's add another feature to it. A lot of times, these gas equations now, they're connected to stoichiometry. So stoichiometry, we saw back in chapter 3, chapter 4, a little bit in chapter 5. This one says calcium carbonate decomposes to yield calcium oxide and carbon dioxide gas. We got a balanced equation for it. If 272 grams of the calcium carbonate was placed in a balloon at standard temperature and pressure, what would the final volume of the balloon be if it completely decomposed? So what this is asking within the setup here, it's saying you're starting with a solid, you're going to make a gas that then fills up the balloon. In this one right here, you don't have to worry about any leftover solid. The gas, that's going to contribute the entire volume. If you have calcium oxide sitting there, you can ignore that. For any of these questions, you're only looking at the gases because they take up so much of the volume compared to any solid. So this is now a stoichiometry problem. You've got a certain amount of the starting material. It's going to produce a gas, and then you're going to use that gas to be able to calculate what the final volume is. So when I say connected to stoichiometry, if we think back, in chapter 3, that's when we first began converting to moles, and we used the molar mass for that. A certain number of grams divided by grams per mole, that was how we could get to the number of moles and use it in a balanced chemical equation. In chapter 4, we could get to moles by using the concentration. Moles per liter times number of liters got me to the number of moles. Concentration times volume got me to the number of moles. We needed moles when we were doing stoichiometry problems. All that we're doing now in chapter 10, we're just adding another way to get to moles. We can get to moles and use moles based now on its description with the ideal gas law. So when I'm saying this type of question is connected to stoichiometry, it's really just a stoichiometry problem that you're asked to do something with the information in a little different way. So this is how I'd work through this one. I would start by saying I need a balanced equation for it. Calcium carbonate is giving me calcium oxide plus CO2 gas. It's telling me I have a certain amount of the calcium carbonate. So I'm going to look closely and see that 1 mole of calcium carbonate gives me 1 mole of CO2. The coefficients are 1 and 1. So I want to make sure and be careful with that one. So then I'm going to ask myself, well, how many moles of the reactant did I start with? I have a certain mass given. I look up the molar mass, either on the periodic table or in this case, it was provided. This is how many moles now I have of calcium carbonate that I started with. And that will be how many moles of the CO2 gas I can produce, because it's a 1-to-1 ratio based on the coefficients. So the question now is really saying, okay, you've got 2.72 moles of carbon dioxide gas at STP. Tell me what the volume is. This is what I mean where the gas equation is being connected to stoichiometry. Now, at this point, I think you got 2 different ways you can solve it. Many times there's going to be more than one way you can solve these. Here's one way that you could solve it. If you're going to seek to calculate the volume of 2.72 moles of CO2 at STP, standard temperature and pressure. One would be this. You could go back to your picture of PV equals nRT and plug in the conditions that you know. You know it's 2.72 moles. STP is 1 atmosphere. Temperature is 273.15, and you've got your gas constant. You plug those all in, you only got one variable to solve for, which is the volume. That works. That will absolutely tell you the volume of 2.72 moles of CO2 at STP. Nothing wrong with that. If I was on a test, that's probably how I would solve it personally. But I know another approach that students have, it'd be something like this. They say, oh, I've memorized that at standard temperature and pressure, 1 mole of any gas is 22.4 liters. I've got 2.72 moles. How many liters is it now? They set it up like a ratio. That works too. They're just taking what they know about the volume of an ideal gas at STP, and they're applying it there. Both of these lead to exactly the same volume, 61 liters. Now, I would say in this question, this was stoichiometry, where we worked on the stoichiometry, and then we used that to tell us something about the gas. Really common is also going in the opposite direction. I will tell you conditions about the gas, and you use that to determine the number of moles and use that in the reaction. It's just going back and forth between PV equals nRT and number of moles that we used in stoichiometry. So that's another very typical question type. The last one I want to bring up, a little bit different, and it's the ones that involve density. So if I'm thinking about gases and density, let me show you why it's a little bit different, but it still fits together. So we have a description for our gases, PV equals nRT. And we think back, and density is mass divided by the volume. So I could manipulate this a little bit. I don't have mass in the equation, but I could get number of moles over volume. And I can connect number of moles and molar mass together. That's one way that I could get what the mass actually was. So my point is, you could manipulate this. And by using molar mass, you can turn this into the density. Now, this kind of equation and trying to make it all fit together in one time, that's not how I really think about it. Okay, that's not how I don't try to come up with just one expression. I think about it in stages a little bit. And let me show you my strategy if I'm trying to think about density and the ideal gas law. So here's a typical question at the bottom. What is the density of N2 gas at 130 degrees Celsius and 750 torr? Report your answer in grams per liter. Grams per liter, so a mass divided by volume. So if I think about this, what do I already know? Well, I know the molar mass for N2. I'm going to need that because I'm not interested in just the particles. I got to somehow get it into grams. So the particles that I'm going to be using are N2. So I'm thinking to myself, okay, I know the molar mass of N2. I look it up at the periodic table. 14 plus 14 gets me 28 grams per mole. I also know that I have a relationship describing pressure, volume, number of moles, and temperature. I got my ideal gas law. If I look at that in this equation, what terms do I have? I see a pressure listed, 750 torr. Great. R is a constant. Temperature, I see Celsius, so I can get the temperature. So at this point, I think I'm really close, but I've sort of hit a wall. I've got two variables there. I got both volume and number of moles. I want to get it down to just one variable so I can solve this. So the trick, or the way I want you to think about it, is just assume that you're using 1 liter. You're going to be reporting it in grams for 1 liter anyways. So just make it easy on ourselves. Let's just say, okay, we're going to solve it for 1 liter because that's the ratio that we want to have anyways. As soon as we do that, I think we've got all the terms that we need because we only got one variable left. So here would be my work for that one. Same kind of setup. You see a pattern for how I set these up. PV equals nRT. I've got the volume. I'm just assuming it's 1 liter. The pressure, I'm going to convert 750 divided by 760. That will turn this into atmospheres. The temperature, 273.15 plus 130, that would be the temperature in Kelvin. My R value, 0.08206 liter atmosphere per mole K. So I solve here, and this will tell me how many moles of nitrogen gas I have. Then I'm going to say, okay, what would be the mass of that? I've solved for the number of moles. Now I use the molar mass, and that will tell me how many grams of it I have. When I'm thinking about these density ones, or really any of the ideal gas ones, I do it in stages. One stage is I use the ideal gas expression, and there's only going to be one variable that I'm ever left solving for. I can't solve this if I have 3 variables or 2 variables. Every one of these questions, if you solve PV equals nRT, there is going to be one variable remaining. I solved in this case, the variable was the number of moles of N2. And then the second step is I did something with that. I converted that to grams so I could come up with the density. That's going to work for any of the problems that I've discussed so far. This is how I would solve a density problem involving the ideal gas law. Breaking it really down into 2 parts. One was using the ideal gas law, and one was using the molar mass to get to the actual grams in my sample. Let me add to this one more set of ideas that are, as we begin to move to the second half here of the chapter. What happens if we have a mixture of gases? Everything that we've been looking at so far, it either was air, so we had some, who knows what was there, or it was a specific one. What if we have a mixture? Well, if the gases don't react with each other, we can treat them independently. If they are behaving ideally, it doesn't matter what type they are. All that mattered was the number that we had. So if they don't react together, we can just look at them as a whole collection. This is what I mean by that. So let's say you had a cylinder here and it was holding gas A. The pressure of that was 0.6 atmospheres. What if you had another cylinder that had gas B and it was holding gas B and it had 0.4 atmospheres? Notice in this picture, there are fewer particles of B than A, so that's why the pressure is different. If both of those were in the same container, I could just add them together. I would have now a total of, as they're showing here, like 10 particles, and I would just add together the pressures. If a particle is a particle and it doesn't matter their type at all, as far as contributing to the pressure, I can just add it together to get the overall pressure. This designation here, P, is showing the overall pressure. P with the subscript A, B, or C or D, you can have as many as you want. Those are all called the partial pressures. The partial pressure of A was 0.6. The partial pressure of B is 0.4, because when they're combined, they equal a total of 1 atmosphere, and it's just within those same proportions. Another way that you'll see this is with this notation here, where it has this chi, this x sub A, given this notation here. So what this is designating, that chi, that x, that's what's called the mole fraction. The way that you calculate it, you can calculate it for any of the components, is to say, well, how many of A do you have relative to the total number of moles? How many moles of A is there relative to the whole thing? That would be the fraction of A. You can talk about the fraction for any of them. They're going to add up to being 1. They add up to 100%. Let me show you how we sort of look at this mixture of ones and how it shows up in a problem. Take a second within here. I'll give you a minute to read this through, and then I'm going to show you my work on this. So as I read it through, it's telling me, okay, I've got 2 different types of particles in here. The black ones and the white ones. The filled in black ones and the open white ones. and they're going to represent either HCl or benzene. So if I were to look at these, I definitely have more black ones there. If I count it up, 1, 2, 3, 4, 5, 6, 7, 8, 9 black ones and 1 white one. If I were to think about the fractions that are present there, there's a total of 10 particles. 1 out of the 10 was the open white sphere, which they're calling benzene. So the fraction of that would be 1/10 or 0.1. For the HCl, well, those were 9 out of 10. 90% of it was coming from the HCl. Most of the pressure is going to be coming from the HCl. And when I say most of the pressure, how much of the pressure? 90% of the overall pressure is coming from the HCl. 10% of it is coming from the benzene. It simply has to do with the number of particles that we have, the proportion that we have. So in this particular question, it says that the total pressure is 0.1 atm. Most of that is coming from the HCl, 90% of it, 10% of it's coming from the benzene. To put some numbers on that, 10% of 0.8 is 0.08. 90% is 0.72. The proportions that you have, the partial pressures, they add up to the total pressure. And they're exactly linked with 90% of the particles and 10% of the particles. The way this connects back to this mole fraction idea is this. If you take the mole fraction times the total pressure, that is the partial pressure of that component. 10% times the total pressure of 0.8, that tells me how much the benzene particles were contributing. Same kind of setup for the other one. 90% times 0.8, 0.72, that would be the partial pressure for that one. We're just treating them independently and seeing that they add up to the total amount. That's the idea of looking at mixtures and partial pressure. Now, if we're looking at some problems here, I'm not going to work through this in this set. Let's first of all see if we can classify them. If I'm looking at all of these end of chapter ones, these are all in that first category. These are all using PV equals nRT. I might have to do a unit conversion, but it's clear in each of those cases that I have a variable that I'm trying to solve for. I would call this one some applications of PV equals nRT that involve some unit conversions. These two right here, if I were to classify these, there was a ranking going on or a calculation. These would be involving the density of gases. This one right here, as soon as I see a reaction, okay, this is involving the stoichiometry. And this was the last category involving the partial pressures. We had a mixture of different types and it was asking to calculate the partial pressure, calculate the total pressure. So I'd say those are the different categories that I would expect right here. Typical questions here from the first half of the chapter are applications of PV equals nRT that might involve unit conversions, density, stoichiometry, and partial pressure. Let me send you a polling question on this. Out of this group right here, if you had to pick ones that you want more information on, what would they be? You can select all that apply. Which of these do you think are, as far as your current understanding, what would be most helpful to begin to examine? Take about 10 more seconds if you haven't responded. Okay, so class poll on this one. The the least was saying, well, tell me more about the applications. And then we saw considerably more for these other somewhat more involved. In a way, all of these subsequent ones, they could be applications too, because they might involve unit conversions. But in each of these cases, if we're doing density, stoichiometry, or partial pressure, it seems like we got a little bit more going on. We've got to do something else with the idea. Let me step through, and I completely get saying, hey, show me another example. Let me show you another example or two for these. So first of all, on this density one, let me show you another way that the question could be asked. So this first one right here, A, calculate the density given a particular pressure and temperature, that would be solved exactly like the one that I showed earlier. Part B is different. It's saying instead, calculate what the molar mass would be if its density was 2.50 grams in this many liters. Let me work that one through for you. Okay, so again, I'm going to begin by saying, let me grab PV equals nRT and see what my missing term is. When I grab it, I'm only going to have one missing term. If I put it all together, I have a pressure that I can convert, a volume in liters, my friend, the gas constant, 0.08206, and I can convert the temperature to Kelvin. So I only have one variable in that, which would be the mass, excuse me, which would be the number of moles. I can solve for the number of moles. It's not asking for the number of moles though. It's saying, what is the molar mass? But I'm going to use that. 2.50 grams was this many moles. Molar mass is grams per mole. So I just divide it out. So the particular gas that we're looking at within this one has a molar mass of 80 grams per mole. I think this fits the same framework that I was describing of, let's first use PV equals nRT. And then let's do something with the variable that we solved for. We solved for the number of moles. Now we're using the grams to determine the molar mass. This would be another way that I've seen density problems. How about this one involving partial pressure? So this one's set up as a scenario. It says you take some dry ice, that's what solid carbon dioxide is. You put it into a 10-liter container. And that container already had some air to start with. The carbon dioxide sublimes, which is cool. It means it goes directly from the solid to the gas. And they're asking now about, well, tell me the gases that you end up with. So if I were solving this one, I would start by saying, I want to make a little sketch just so I can get straight with what we're talking about. There was a 10-liter container. It initially had air in it. And to that, I'm going to add 5.5 grams of CO2. So it's asking me about, well, tell me about the final conditions. So let's first take care of that air. And you know that how I'm going to do that. I'm going to say, I'm going to set up PV equals nRT and see what my missing variable is within that. I'm going to write PV equals nRT. The pressure, by doing that ratio, gets me into atmospheres. It's a 10-liter container. I know what the temperature is. I know what R is. I can figure out now the missing variable, which would be how many moles of air were in that sample. That takes care of everything in terms of the air. How about in terms of the CO2? Well, I can use the molar mass there to figure out how many moles. CO2 is 44 grams per mole. So now I can figure out how many moles of CO2 I added. What it's asking for is, what would be the partial pressure of the CO2 and what would be the total pressure that I have? In order to determine the partial pressure, I can just look at it independently. I don't have to worry about the gas interfering with another gas particle. So I can just use that straight out with PV equals nRT in terms of the CO2. It's in a 10-liter container. I know the number of moles that I have, gas constant R, and I convert the temperature, 24 plus 273.15. This will be the pressure that I have for the CO2. That's considered the partial pressure because there's pressure in that container from something else too, from the air. That's why we call it the partial pressure. It's contributing to the total pressure, but notice I just treated it independently because that's what we can do. We can treat our gas particles independently. When it asks for, tell me about the total pressure, well, it's going to be coming from two different things. It'll be coming from the CO2 and it will be coming from the air. That's what will contribute to the total pressure. We could look at it in different ways. I decided just to take that pressure of the CO2 and think about it in terms of torr, because this first one was already given in terms of torr. Adding up the contribution from the air and the CO2, that gets me the total pressure being exerted here in the container. I treated them independently, added up to get to the total value, and in stages, those would have been the partial pressures. If I'm thinking of last example for y'all in terms of stoichiometry, this one's very similar to what we worked a moment ago. And I know what the key mistake is students would make on this one. It has nothing to do with the PV equals nRT portion. I know the key mistake is not paying attention to the coefficients in the balanced chemical equation. This one's set up where it's saying you want to make a certain amount of H2 gas. Okay, how much of the reactant do you need in order to make that happen? You want to make enough H2 gas to fill up 145 liters at 825 torr and 21 degrees C. How much of the calcium hydride do you need to do that? This is giving us gas conditions in order to determine the number of moles. So if I were to solve this, I'd say, okay, I need a balanced equation. I'll plug in everything in PV equals nRT. This will tell me how many moles of H2 do I need. That's the only variable I have left. Once again, I'm starting with the ideal gas equation and then I'm doing something with it. I figured out the number of moles of H2 I would have. And then I'm just looking back to the balanced equation and asking, okay, how many grams of the reactant would I need? I've used the ideal gas equation to see that I need 6.5 moles of it. 1 mole of the reactant gives me 2 moles of the product. The reactant is 42 grams per mole. That will tell me how many grams I need of the reactant. This is now connecting again, PV equals nRT with moles and stoichiometry. Now, so we worked through, I'd say 4 representative calculations twice. Those are all in this first half of the chapter, all the way through 10.6. When we get now to this bottom part, we're now going to look at what's called the kinetic molecular theory and see how that fits together with the ideal gas law. So we had this one within a pre-class video. This idea here, if we were to compare these two, they had different densities because they had different masses. Density was a factor that would affect the mass was something that would affect the density. But the number of particles, that's all we needed for the pressure. Density is affected by the mass, pressure is not. Would there be other properties that would also be affected by the mass? That's what we're going to want to try to think about. Now, what we're doing here is we're looking at what's called the kinetic molecular theory. That's used to explain the ideal gas law. It explains it by saying those relationships within PV equals nRT, they come about if you think about gases as having these characteristics. Now, what I'm going to do is I'm going to step through these characteristics. On an exam, you're not going to have an essay where you would say, oh, well, let me write down all these details. But very typically, there's an exam question that's asking about these features of the kinetic molecular theory. I don't want you to say, oh, well, let me memorize these bullet points. That wouldn't help a bit. I want you to try to think about what these are describing, because I think you're going to be able to remember it that way. These are what are describing an ideal gas. An ideal gas that follows PV equals nRT. Many, many gases come really close to that. So is it an ideal approximation? Yeah, but many, many gases could be described as having these characteristics. A real gas is one that begins to deviate from this. So when we look at these features, let's see what this means to describe a real gas and when they would begin to break down and no longer be applicable. So first of all, when we're thinking about gases, we could have a large number of particles that are bouncing around within our container. But even though we have a large number of gas particles, most of it is empty space. These are the assumptions within the kinetic molecular theory. So first thought, this would begin to break down if it wasn't mostly empty space. If it was squeezed into a really small volume, if the pressure was really high, it would not be behaving very ideally. This is one way that the ideal gas law turns it into a real gas, is if the pressure gets really high, the volume gets really small. Now, when we're looking at the motion, let's add some containers here. So if you choose a particular one of these and really focus on it, and you track its motion, try to follow one. I'm still doing a good job with mine. Still got it. Usually I lose track, but I was focused pretty good on one. Okay, I lost it right there at the end. If I'm looking at those features, the particle that I was looking at, it was always moving in a straight line. It could bounce off other particles, it could bounce off the walls, but it was always traveling in a straight line. That's because there are no attractions and repulsions. These gas particles do not interact with the other ones until they collide with them. There are no attractions and repulsions. Another way of thinking about it, there's no potential energy. There's only kinetic energy in an ideal gas. There's only the energy of the particles as they're moving around. There are no forces. There's no gravity acting on these. There's no electrostatic attractions. There's no attractions or repulsions. They're like billiard balls, just moving along in straight lines. If they strike each other or they strike the wall, they can ricochet off. They can transfer energy between each other, or they could exert energy when they could exert pressure when they strike the wall. When they're doing that, they never run out of energy. It's not like they bounce into each other and they lose energy and then they're all sitting at the bottom of the container. When the idea is that they're perfectly elastic, you can just keep having these transfers taking place again and again. And the pressure results when these are striking the walls of the container. Now, another thought of when might this break down? We said that there are not attractive forces present in this ideal gas. When might you have attractive forces be relevant? If the particle motion slowed way down and the temperature was quite low and the particles were close together, then the attractions could begin to take hold. So this is another way that the ideal gas model breaks down. If it's at a really low temperature, it's no longer applicable. I've seen this kind of question on exams asked this way. When is a gas most ideal and when is it least ideal? A gas is going to behave most ideal and follow these guidelines here, or be consistent with those, when the pressure is really low and the temperature is really high. They've got plenty of empty space and they're bouncing around quite freely. It's going to become more and more real and deviate from the ideal gas law if the pressure is high, if they're squished together and they're in a very small volume. Now, if we're looking at these and we're thinking about the particle motion and the temperature, particles are all moving around. If we remove heat and the particles slow down, I see the speed is going down and their kinetic energy is going down. The temperature is going down. If I take the same one and I add heat to it, I see the thermometer goes up, pressure's going up, kinetic energy is going up, the speed's going up. When I've said that the particle motion, that's what the kinetic energy is describing, that's what the thermometer is describing, this is the mental image that I had in my head right there. If you increase the temperature, you're increasing the speed, you're increasing the average kinetic energy. What if you did the same thing here, but you made it so the pressure was going to remain constant? So let's add some particles to our container. They're all bouncing around. I see the thermometer, I see the pressure gauge. Now, before adding heat, I'm going to make it so the pressure has to stay constant inside the container. If I reduce the particle motion, notice how it's contracting here. This is like when we put our balloon into the liquid nitrogen. We reduced the temperature, heat left the system, and we saw this contraction. In order for the pressure to remain constant, it had to squish smaller. We can certainly cause it to expand once again by heating it up. In order to remain constant pressure, the volume has to increase. What we're trying to do is think about what does it mean to have the particle motion, and how does that now explain the aspects that we saw in the ideal gas law. Getting and wrapping up here with a new idea for us. This was one that I posed in the video. What happened if we took 6 heavy gas particles, excuse me, 60 of these, and we're going to add another 60, but now they were going to be lighter particles. If we were going to double the number of particles, we initially had heavy ones, and now we're going to add light ones. What's going to happen to the pressure? Let me send you a poll on that. So we initially have 60 that are heavy. We're going to have 60 that we add that are going to have that are going to be lighter, smaller mass. What's going to happen to the pressure? Initial responses for that, it's going to double. So the initial response, we're saying, okay, if you double the number of particles, you're going to double the pressure. I like that thinking. Okay, I think if I double this, it will double, because we just said we can treat them independently. We could think about the pressure for the lighter particles. We can think about the pressure for the heavier particles. Notice in these equations, there is nothing about the mass. We're just saying that the total pressure has to do with the total number of particles. The total pressure, that's the sum of all the partial pressures that we have. It only depends on the number of the particles, the N. It doesn't depend on their mass. Let me skip past this one because I want to give you a visual for what's going on here. It's something we could work on next time, but I want to show you what the concept is. In this case, we just said that it's only the number of particles that's important. It doesn't matter if they're light particles or heavy particles. They can exert the same pressure. They can have the same kinetic energy. So how does that happen? Okay. So let's start out. Let's first add heavy particles. These are what we tracked before. I mean, if you were to pick one of these heavy particles and try to track it, I think you'd do a decent job. Now let's add 60 lighter particles. Good luck tracking those, okay? Much more difficult to track those. What we're seeing here is both the heavy particles and the light particles, they can exert the same pressure, but in a way they exert that pressure differently. The lighter particles, in order to have the same kinetic energy, 1/2 mv squared, they got to be moving at a much higher velocity. They got to be zipping around much more than the heavier particles. So a heavier particle is a little bit more plodding. It can strike the wall and exert the force. The lighter particle, it is bouncing into the walls very frequently, but it has to have a much higher velocity in order to exert that same pressure. It leads me to have these two summaries that are shown within the book. These are, I think, quite striking. So this one at the top right here, this is showing the distribution of speeds and how it relates to the mass. Notice that within here, H2, that is a much lighter molecule than O2. For the same temperature, the same average kinetic energy, those lighter particles have to be traveling at a much higher speed than the heavier ones. It's given this broad distribution because we saw within the simulation, it's not like they're always fast or always slow. Some moments they might be going slow, some they're going fast. That's why we get this broad distribution. But we see that the mass is really important. A lighter particle has a much higher average speed than a heavier one for the same kinetic energy. In both of those cases, if you increase the temperature, you increase the kinetic energy, but the mass here, crucially different. Two ways that I saw this within end of chapter questions. Here was one. It gave two different curves and said, okay, if they're at the same temperature, which one's H2 and which one's O2? The way I'd answer this is say, oh, the lighter particle would have the higher speed distribution. If it was those same profiles and you said, well, what if they're now the same gas but at different temperatures? No problem. Higher temperature means a higher speed profile. These are implications of where our kinetic molecular theory takes us. Really great job paying attention this evening. We got about one more idea to wrap up within chapter 10, and then we'll have some time, next period, quite a bit of time to move on to chapter 11. I'll be hanging around for questions. Once again, I really appreciate your attention.